so today's notes. This is sample means, so sample proportions. So I am going to write the same description of a sample distribution except using means now. So we can go back to our homework. And this equation, or this sentence that was a definition, I'm essentially writing that, but with specific to means. So it's specific to proportions. So here, a sampling distribution of x bar is the distribution of what? I know that this specifically, as opposed to approximate, is using what? All values each one of our dots now is going to represent a what? A mean. That you would write out in context a mean what? And what's the big specific between the difference of a sampling distribution and an approximation of a sampling distribution? What is the difference between a full sampling distribution versus an approximation? In whatever our individuals are. So this goes back to where we started on day one with yellow versus blue, and which sample, each sample had a proportion of yellow. We could do that same thing and find the mean for each of those samples, and then create a graph of all the dots, and each of the dots be a mean. So this first one, you should essentially be able to do on your own without my help, even though we've never written it. So yesterday, the day before, mean of the sampling distribution of p hat. Now we're dealing with the mean of the sampling distribution of x bar. So what symbol is that going to be? Of what? Of x bar. Well, what did mu of p hat equal? So what does mu of x bar equal? So that concept goes exactly the same. So that's the mean of my the sampling distribution is the same as the mean of the population. So that's the unbiased part of it. Now, here the equation is different. We know that it's going to be sigma of what? So sigma of x bar actually equals sigma over square root n. And this is where, if you don't know what symbols are, this starts to get confusing, because how can a sigma equal a sigma? Well, those are two different things. What does just sigma stand for? What does sigma stand for? Population standard deviation, where this is instead the standard deviation of the sampling distribution of x bar. And then just like usual, we still have to do the because 10% condition. We're still accounting for error. If we get too close, then we're accounting for too much error. Alright, so this whole section is talking about what we just talked about with the last slide of the other notes. So the exact same concept works here. The mean of this, or the sample mean, is unbiased estimator of the population mean. The values of x bar are less spread out for larger samples. So a sample that is 4 times larger cuts the standard deviation what? In half. A sample that is 9 times larger cuts it to a third. And what we just wrote, we can only use the standard deviation formula when the population is what? At least 10 times as large as the sample. Very generally speaking here, I don't know what GPA goes to now. Something like this. If I take a sample of people and I put a dot on this graph for their GPA, are all of my dots going to be similar? No. Are they going to be at a specific place on this graph? Are they going to be at a specific place on this graph more often? Am I going to get some people that have a GPA down here? Yes. Am I going to have some people that get a GPA up here? Yes. Let's say I instead go take samples of 50 people. Am I going to get a random selection of 50 people from this school where their average is there? Is that very likely? No. So, very generally speaking, what I thought did look like this, now when I take samples of 50, is going to look how different from that curve? It's going to do this, right? It's like it's probably still going to follow the same thing, but just squeezed in. Does that make sense? So if I take more samples, or if I take samples of a group instead of individuals, those extremes that were out here aren't going to be seen as much. It's definitely going to condense it a lot, which is kind of what that was saying. So averages are less variable and more normal, which is part I haven't talked about, than individual observations. All right, so let's pretend that this top distribution is the population, the entire population. What can you tell me about that entire population? What can you tell me about this distribution? It is symmetric. So if I sample from that same population, so here I'm going to sample 5 at a time, and here I'm going to sample samples of 20 at a time. Can't go higher. 25 at a time. As I sample, so I'm showing you what, so like I'm sampling 5 and then put a dot there. I could sit there and keep doing different dots. That's 5 different samples, 10 different samples, 15, so forth. As I'm sampling from these, regardless of if I'm taking a sample of 5 or a sample of 25, what do you notice? So regardless if I'm taking a sample of 5 or a sample of 25, what do you notice about both of those? The what? Mean stays the same. What else? Not a lot of extremes. What else? How about compared to up here? Less spread. Which one has less spread? The one that has a bigger sample size. What about shape? Pretty symmetrical. Now, that's not perfect, obviously. So let's say we switch, and let's come up with a distribution that's what kind of distribution do I have now? Right skewed. So if I do the same thing, I'm sitting here taking a whole bunch of samples. What do you notice about the sampling distribution approximation when I'm taking samples of 5? What about that shape? What is this shape? Kind of symmetrical, but still a little right skewed, right? What about this one? It's pretty symmetrical at this point. So when my sample size is low, what is the trend of my shape going to be? It's going to follow the population. But regardless of what's going on, as my sample size gets bigger, it's going to start to do what? It's going to get fairly symmetrical, which is part of what that is saying. All right, so first problem says the length of human pregnancies from conception to birth vary according to a distribution that is approximately normal. It gives us that. With a mean of 266 days, that's our what? And this is our what? Sigma. So one thing I do want to write beside of this, though, is this says find the probability that a randomly chosen woman. That is very, very, very specific and something that at this point you probably would not notice. So I am here talking about an individual. This has absolutely nothing to do with Chapter 7. Could I have answered that question in Chapter 2? So if this were a Chapter 2 question, what is my symbol that goes here for an individual? So this is just the probability that X is what based off of what it says. So this problem right here is an individual which has absolutely nothing to do with Chapter 7. So we just take this, convert this to a what? Divided by what?
60.
This gives me 4. 4 divided by 16, which gives me 1/4. And then 270, which gives me 0.25. So I can use my calculator for the easy way. Normal CDF, my lower bound is 0.25, my upper bound is positive infinity. If anybody hasn't got calculators that are up here, I don't know if that's broken them. And what do I get as my probability?
0.4013.
If I am dealing with something with a mean of 266 days, the standard deviation is 16, does it seem unreasonable for me to get something of 270 or higher? No, not at all. It happens about 40% of the time. So now we're going to make the exact same connection, but to today's. So now we're going to have a simple random sample of 6. So this is my what? And it even defined X bar for us, so we don't have to find mu. So what is the mean and sampling distribution of X? That should be really easy. What do I write? Which equals? And then go ahead and leave your units with it for now. It says compute standard deviation of sampling distribution of X bar. Check conditions are met to use this formula. I don't care if you do the equation or the condition first. So we're checking 10% condition. What is 10% condition? What is my lowercase n? It was embedded in part B. So capital N has to be greater than or equal to 60. So there are at least 60 what? And that's kind of a weird one to say. It actually talks about human pregnancies at one point, and it's not necessarily that are pregnant, but that have been. So like I would be pretty lenient with what you put there as long as you're saying the right thing. And then so I could use that to now use my equation. So sigma of x bar equals what? Sigma over square root n. What is my sigma?
60.
Divided by square root of 6, right? Which gives us and let's go ahead and keep 4 decimals because we've been pretty consistent with that. Say again. Is it 5320?
Yes.
And again, I'm just keeping my units for now.
So would you still write because 10%
Oh.
information there?
I would, for my habit, if it were a problem where it like literally asked, why do you do it? So now do it. I wouldn't cut off for it, but out of my habit, I would. Yeah. Alright, so D, this is something that we have not come across like this yet. What is the shape of the sampling distribution of x bar? What is the only thing I had to go on in this entire problem that has anything to do with shape? What did it tell me way back here? What is approximately normal? Of so our population distribution was approximately normal. Well, that goes back to what we just did with this example. When this one looked like that, what happened regardless? It stayed similar. So if our population distribution originally was told that it was normal, then we're also going to be able to use a normal approximation here. So it was stated that, and again, you have to know that what was normal, the population distribution. And this one specifically said that the population distribution was approximately normal, right? Just go with wording there. So if it says that, that means I'm also going to follow. So this one is obviously the easiest method when we have to check our normal condition.
Will it always be population distribution?
Yes. Alright, so E asks, what did A ask? Greater than 270?
Yes.
Let's just switch that to make it the same. And then we have to do one less Z-score. So I'm asking the exact same question, but now what's different? I'm doing it for the mean of a sample as opposed to just for one individual. So A is chapter 2. When I'm given a sample and I want to find if that sample is there, it's chapter 7. And chapter 7 means 4-step process. And yesterday if it were one like this and we had already answered some, we didn't rewrite it back out as a 4-step process. But I want to today, and I'll show you how you do it if you've already done some of it. It makes it really easy. So state, what's my first part of state?
Population.
What is my population here?
Pregnant woman.
I don't care if you add the word all, I just tend to most of the time. Again, this one was worded weird. Human pregnancies was one of it. Women who were pregnant. Just make sure you're talking about them in general. So our sample, this was very vague. So what would I say for my sample? The randomly chosen pregnant women. What's next? Well, mu is going to stand for what word? What does it say? This is the mean what? Does it? I don't remember if it says length. That would make sense. Length of pregnancy. And then the last part is what I want to find, and I want to find here, P parentheses what? Now, what went here yesterday? P hat. So what's similar to P hat? X bar. So we want to see if where our sample falls. So our sample greater than 270.
Are we doing all the 4 steps or just state?
We're doing all the 4 steps, but we've done most of it already. So plan, what is required in plan?
10% condition.
Where was 10% condition? Part what? What's our other condition? Where was that one? So I can still do a 4-step process. Most of it I'm just saying, hey, it's up there. Even the beginning of do was in what 2 parts? What, B and C? Is that right? So I could rewrite those, but I don't need to. The mean and the standard deviation. So I can go straight to what? Now I still have to do part of do.
Oh, yeah.
I'm using part of that, but then I'm starting where within do. Sorry, that was F. That X bar is, and I can go straight from there and finish. So I do what with that? Convert it to a Z. So now it's going to be 270 minus what? But now it's going to be, as opposed to part A, it's going to be divided by
Not there is you score. Those were squished on the top.
it's value minus mean. Our mean is 266. Our population mean. And now somebody asked me maybe yesterday about writing out the equation. The reason I'm choosing to skip writing out the equation is yesterday it was P hat minus mu of P hat divided by sigma of P hat. And then now it's X bar minus mu of X bar divided by sigma of X bar. And then in part A, it would have been this. But I've already written somewhere on the paper for every single one of them what those stand for. And then I plugged in the right number. So I'm showing that I know what goes there without having to also do this and confuse myself. And that's why I'm choosing not to also fill in that. It's always value minus mean divided by standard deviation. And what do you get as that Z value? 0.61. And then so I can use this in the calculator. I don't have this because I changed my numbers from what the problem said. I don't know if this one ends up in.
You type in 1E99.
So this is your lower, and then 1E99, yeah. And what do you get for that?
0.279.
So how does our answer for A compare to our answer for E? Our answer for A is definitely what?
Greater.
Because it is more likely to see a single individual stray from the mean than the mean of an entire group stray that far from the mean. And then conclude I'm just going to write it up here. What would our conclude be? Where does it start? How many? 6 what? When what?
The mean of
And technically it's also, but if you do this part, I'm not going to count off if you don't do that part. Then the probability of getting a sample. Oh, because I changed it. Sample mean of more than 270 days. 0.2, what was it?